some more examples. Let us study a definition, that is conjugate pair. Conjugate pair. Conjugate pair is a pair of acid and base which differ only in one proton. That is a pair of acid and base. Pair of acid and base. And how are they related? They differ only in one proton. So a pair of acid and base which differs only in one proton. Only in one proton. So the difference is only one proton. You know, acid is proton donor, while base is proton acceptor. That is Bronsted concept, Lowry-Bronsted concept. Now you take a pair of acid and base, which differs only in one proton. So let us take a very common example familiar to us. Say hydrochloric acid, HCl. It ionizes giving H plus ion and Cl minus ion. H plus ion is our proton, hydrogen ion or proton. So HCl gives proton and Cl minus ion. So by definition, HCl is an acid because HCl ionizes, dissociates giving proton or H plus ion, hydrogen ion. So it is an acid. You think of the reverse reaction. That is chloride ion, Cl minus ion plus H plus ion giving HCl. The backward reaction. You take the reverse reaction. If the reverse reaction occurs, the backward reaction occurs, in the reverse reaction, backward reaction, Cl minus ion can accept a proton to form HCl. So Cl minus ion, chloride ion is a proton acceptor. So by definition, chloride ion is a base. Chloride ion is a base. That is a Bronsted base, because chloride ion can accept a proton. Now we have got a pair of acid and base. On the left hand side there is an acid HCl. On the right hand side there is a base Cl minus ion, chloride ion. And you compare these two. They differ only in one proton. So the difference between the acid and base pair is only one proton. Such a pair of acid and base, which differs only in one proton, that is a conjugate pair. So here HCl and Cl minus, that's a conjugate pair. Cl minus ion is the conjugate base of a HCl, while HCl is the conjugate acid of a Cl minus ion, Cl minus. So they differ only in one proton. Let us take another example. You take H2SO4 sulfuric acid, H2SO4. H2SO4 can dissociate in two ways. Either say H plus ion plus HSO4 minus ion. This is one way of ionization. Here the ionization is not complete. You can take another dissociation, complete dissociation, ionization, giving 2H plus ions plus SO4 minus 2 ions. Let us see the case of the acid and base. You take H2SO4 and consider the forward reaction. In the forward reaction, H2SO4 gives a proton, H plus ion, hydrogen ion. So by definition, H2SO4 is an acid because acid is a proton donor. So acid is a proton donor in the forward reaction, the forward change. So H2SO4 is an acid. You take the backward change, that is HSO4 minus ion, hydrogen sulfate ion, plus H plus giving H2SO4 back. So in the reverse change, HSO4 minus ion is acting as a base because it can accept a proton. It can accept a proton. Similarly, you come to H2SO4 again, the last equation given. In the forward change, H2SO4 is acting as an acid. Backward change you take, SO4 minus 2 ion is acting as a base. A base. Now, you say which is a conjugate pair? H2SO4 and HSO4 minus, or H2SO4 and SO4 minus 2. Which is a conjugate pair? Vidur, can you try? Vidur, you try. Which
H.
is a conjugate pair?
First one.
You show me using your fingers. If it's the first one, yes. Yeah, this is the conjugate pair. That is the conjugate pair. Because the difference between the acid and base is only one proton. So H2SO4 and HSO4 minus ion, that is a conjugate pair. So we say HSO4 minus ion is the conjugate base of H2SO4, while H2SO4 is the conjugate acid of HSO4 minus ion. While in the second case, we have a pair of acid and base. We have a pair of acid and base. But the difference between the acid and base is not one proton. The difference is 2 protons. So H2SO4 and SO4 minus 2 is not a conjugate pair. H2SO4 is an acid. SO4 minus 2 ion, sulfate ion, is a base, that I agree, but that is not a conjugate pair. So a conjugate pair differs only in one proton. Such a pair of acid and base is called a conjugate pair. Let us take some more examples. You take NH4 plus ion, ammonium ion. When ammonium ion dissociates, we'll get H plus and NH3 ammonia. In the forward change, NH4 plus ion, ammonium ion, gives a proton. So NH4 plus ion is an acid. While you take the reverse change, the backward reaction. In the backward reaction, NH3 ammonia can accept a proton, and the proton acceptor, that's a base. So ammonia is a base. Now we have a pair of here we have a pair of acid and base, NH4 plus ammonium ion and NH3 ammonia, and it constitutes a conjugate pair because the difference between these two, that's only a proton. So the conjugate base of NH4 plus is NH3. The conjugate acid of NH3 is NH4 plus. We can take one more example. Say CH3COOH, acetic acid, ethanoic acid, and it ionizes, giving H plus and CH3COO minus. This is our acetic acid, vinegar, acetic acid, vinegar, ethanoic acid, churka, and CH3COO minus, that is the acetate ion, nitrate ion, sulfate ion, hydrogen sulfate ion, HSO4 minus, carbonate ion, CO3 minus 2, hydrogen carbonate ion, HCO3 minus, similarly CH3COO minus, acetate ion. Now, in the forward change, say here acetic acid, it is acting as an acid. You take the backward change. In the backward change, acetate ion combines with the H plus ion, giving acetic acid. So CH3COH is an acid, while acetate, that is a base by definition. And CH3COH and CH3CO minus, that is a conjugate pair. The conjugate base of acetic acid is acetate ion. The conjugate acid of acetate ion is acetic acid. Okay. If you are given a molecule or an ion, and if you are asked to find out the conjugate acid or a conjugate base, then what you have to do? Say the difference between the conjugate acid and base, that is only one proton. Okay, let us take one example to find out the conjugate acid and the conjugate base. Let us start with ammonia, NH3. How can you get the conjugate base? How will you get the conjugate base? Okay, I shall help you. Say acid, you take this one, HX acid, giving H plus X minus. This is acid and this is base. X minus is the base. So how to get the conjugate base? How do you get the conjugate base? The conjugate base is obtained by subtracting one H plus ion from the acid. Similarly, to get the conjugate acid, you add one H plus ion. Say, to get conjugate acid, what you have to do? Say, from a molecule, from an acid, minus one H plus ion, that will give you the conjugate base. Conjugate base. Minus one proton. See here? Acid minus one proton. You will get the conjugate base. Then the base plus one proton. See here this reaction. Base one proton. That will give you conjugate acid. That is the rule. So to get the conjugate base, what you have to do? You have to subtract one H plus ion. Then the product is a conjugate base. If you get a conjugate acid, you can add one proton, then you will get a conjugate acid. For example, you take NH3. How will you get the conjugate acid? How do you get the conjugate acid? To get the conjugate acid, what do you have to do? You must add one proton to that. So NH3 plus one proton, H plus. Then what is the product obtained? NH3 plus H plus. You will get NH4 plus ion. So, and this is the conjugate acid. This is the conjugate acid. Conjugate acid of NH3. Similarly, you are given NH3, and you are asked to find out the conjugate base. Conjugate base, see here, conjugate base. How is it obtained? From the given molecule, you subtract one H plus. So minus one H plus, and that will give you the conjugate base. If one H plus is subtracted from NH3, what is left? NH2 minus. That is the amide ion. NH2 minus. Charge should be balanced, neutralized. So, NH2 minus. And therefore, NH2 minus is the conjugate base. Conjugate base of NH3. Conjugate base of NH3 is equal to NH3 minus 1H plus. That is a NH2 minus ion. Conjugate acid of NH3 plus 1H plus ion. That is a NH4 plus ammonium ion. That is the conjugate acid. You can take so many examples like this. You take, for example, the reaction between H plus ion and water molecule H2O. Say H plus ion is present in aqueous solution of acids. In aqueous solutions, water solutions of acids, there will be H plus ions. And the H plus ion combines with the water molecule with the formation of H3O plus ion. H3O plus ion. And this ion is called hydronium ion. That is a hydronium ion. The question is, what is hydronium ion? What is the charge of a hydronium ion? It is not a hydrogen ion. It is not a hydrogen ion. Same hydrogen ion. That is equal to H plus ion. Hydride ion. Don't have any confusion. Hydride ion is equal to H minus. That is a hydride ion. H minus ion, hydride ion. Hydrogen ion, H plus ion. Here it is hydronium ion. So what is hydronium ion? H3O plus ion. How is it formed? Hydronium ion, how is it formed? By the reaction between hydrogen ion, H plus ion, and H2O. So H plus H2O giving H3O plus ion. Actually, in aqueous solutions of acids, there will be hydronium ions. Instead of free H plus ions, there will be hydronium ions, because free H plus ions are not stable. So the hydrogen ion formed, H plus ion formed, immediately combines with the H2O molecule forming hydronium ion. So in aqueous solutions of acids, there will be hydronium ions, H3O plus ions. So that is about the Bronsted acid and base. So what is Bronsted acid? Sharon, can you help me? What is Bronsted acid? Alvin, Alvin Benny, can you help me? What is Bronsted acid? Bronsted acid. Sharon is not there. Alvin? No. Okay. Bronsted acid is proton donor, H plus ion donor, while Bronsted base is H plus ion acceptor or a proton acceptor. That is a Bronsted acid, Bronsted base. Now let us see another concept. That is a Lewis concept. Lewis concept of acid and base. It is the electronic concept. Electronic concept. Electronic concept of acid and base. Lewis acid and base. Lewis acid and base. Say Lewis concept is based on electrons. There are certain molecules or ions which are electron deficient, and they can accept electron pairs. They are electron deficient and they can accept electron pairs. And the electron pair acceptors, electron pair acceptors, they are acids. That is the electronic concept. Electron pair acceptors are Lewis acids. There are certain ions or molecules which can give electron pairs. They are electron rich. They can give away electron pairs. They can donate electron pairs during reactions. And such electron pair donors, and they are bases. Electron pair donors are bases. Electron pair acceptors are acids. Electron pair acceptor is electron deficient. There will be less number of electrons. They are electron deficient. That's why they can accept electron pairs. While electron pair donors, they are electron rich. There will be lone pairs of electrons. Lone pairs, L-O-N-E, lone pairs of electrons. Say, for example, you take say molecules like BF3, AlCl3, FeCl3. You take such molecules. These molecules are electron deficient. They can accept electron pairs because the central atom has not completed the octet. You take the structure of BF3, the structure of a BF3, it is like this. Now you consider the boron atom. The boron atom. Around the boron atom, there are only 3 covalent bonds. In a covalent bond, there is a pair of electrons, 2 electrons. So 3 covalent bonds, 3 into 2, 6 electrons. That means BF3, in BF3, boron has not completed the octet. So boron is electron deficient. It can accept a pair of electrons, 2 more electrons to complete the octet. So this is electron deficient. Similar is the case with the AlCl3 and the FeCl3. AlCl3, the structure, similar way. See? Or FeCl3, the central atom, metal atom, has not completed the octet. It has to get 2 more electrons. It can accept a pair of electrons. It is electron deficient. And so, by definition, FeCl3, AlCl3, BF3, all these are Lewis acids. Electron pair acceptors. And so these are Lewis acids. You take a BeCl2, BeCl2, that is also a Lewis acid. Say BeCl, Cl, only two pairs of electrons around beryllium. Two pairs, two covalent bonds. So two pairs, only four electrons. It can accept four more electrons, two pairs. So by definition, BeCl2 is Lewis acid, Lewis acid. Now, electron pair donors, they have lone pairs of electrons. For example, you take NH3 ammonia. In ammonia, nitrogen has a lone pair of electrons. We take water molecule H2O. In a water molecule, on the oxygen atom, there are two pairs of electrons. You have studied this even in the 10th standard. You take the structure of ammonia, say NH3, H3, and on the oxygen atom, there will be a pair of electrons. Sorry, no, not oxygen. Nitrogen atom, there will be a pair of electrons. That is electron deficient. There will be non-bonding electron pairs, and that can be given to the electron deficient molecule. So by definition, NH3, it can donate a pair of electrons, and therefore by definition, NH3 is a Lewis base. You take water molecule H2O, say HOH, HOH. On the oxygen atom, there are two lone pairs of electrons. So oxygen can donate electron pairs. So H2O is an electron pair donor. By definition, H2O is a Lewis base. So Lewis acid, electron pair acceptor, Lewis base, electron pair donor. So there will be the electron pair acceptor donor relation between acid and base according to the electronic concept of acid and base, or the Lewis concept of acid and base. You take the reaction between ammonia and say BF3 molecule, reaction between these two. There will be a lone pair of electron. Then what happens? There is formation of a, say, bond between NH3 and BF3 like this. And for the bond, the electron pair is given to boron from nitrogen. See, the structure will be like this. Hydrogen, 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 and here there is a BF3. See, like this, BF3. The donation of electron pair can be shown by a small arrow like this. Small arrow. The arrow head is towards the electron pair acceptor, and such a bond is called a coordinate bond. That is a coordinate bond. Coordinate bond. So coordinate bond is also a covalent bond. There is a sharing of electron pairs. That is also a covalent bond. But in the coordinate bond, the shared pair of electrons, is donated by any one of the atoms. The shared pair of electrons is donated by any one of the atoms. And such a covalent bond is called a coordinate bond. That is a coordinate bond. Okay, next year we have to study coordination complexes. Coordination complexes. Can see that in the coordination complexes, there will be coordinate bonds like this. So remember, coordinate bond is a special type of a covalent bond in which the shared pair of electrons is donated by any one of the atoms. Usually in the covalent bond, the shared pair of electrons is due to the equal contribution 50-50 basis, one electron each from the combining atoms. But in the coordinate bond, the electron pair will be supplied by any one of the atoms. the electron-rich atom, the electron-rich atom, electron surplus atom provides the electron pair, and it is acting as the donor, while the other atom is acting as the acceptor. See, in this case, NS3 is the donor. It is the donor atom, while boron is the acceptor atom. Acceptor. You have to study this the next year in the chapter coordination complexes. There is a donor-acceptor relationship. Okay. So that's about the electronic concepts. Now, let us take another point, ionic product of water. Ionic product. Ionic product of water. And it is shown by Kw. It's a constant. It's a constant. That is why we use K. W, that is for water. So, ionic product of water is a constant. It's a constant for water. And what is ionic product? You know, water can slowly ionize. It can weakly ionize. W-E-A-K. Not a W-E-E-K. That is once in a week. Not once in a week, water is ionizing. Feeble ionization. Weak, W-E-A-K, weak ionization. And water ionizes like this, giving H plus OH minus ions. When water ionization is very low ionization, very weak ionization. And even then there is ionization. Slight amount of ionization is there. And by the ionization we'll get H plus ion and OH minus ion. Now you consider the forward reaction. In the forward reaction, H2O is acting as an acid or base. Gauri, forward reaction, H2O. There is a pair of acid and base here. Here there is a pair of acid and base, which is acid and which is base in this case. Protic acid, the
H2O is acid.
proton is acid. So which is acid in this case? H2O is acid, this is acid. And the reverse change, OH minus is acting as the base.
Base.
It is acting as the base. I simply asked you, that's all. And that's a conjugate pair. It's a conjugate pair. Okay. Now, the ionization, I told you, it's very low ionization, weak ionization, feeble ionization. And there is equilibrium. Suppose equilibrium is attained. At equilibrium, what about the concentrations of the ions? The concentrations will remain the same. Remember, the concentrations will remain the same at equilibrium. Now, at equilibrium, you take the product means into here, the product between the concentrations of H plus ions and OH minus ions present in pure water. And that's called the ionic product of water. So ionic product of water, Kw, is equal to, that's a constant. It is the product of the concentrations of H plus ion and OH minus ion, product, it is product present in pure water. And that is the ionic product of water. So ionic product of water is the product of the concentrations of the ions, product of the concentrations of the ions. Which ions? H plus ions and OH minus ions present in pure water. And that product is called the ionic product of water, and it is a constant. And this is a constant. And it depends upon temperature. At 298 Kelvin, ionic product of water Kw is equal to 10 raised to minus 14 mole square per liter square. That is a ionic product of water. See, concentration of H plus, that is equal to 10 raised to minus 7 mole per liter. OH minus, same value, 10 raised to minus 7 mole per liter. Therefore, Kw is equal to concentration of H plus 10 raised to minus 7 molar means mole per liter into the other one 10 raised to minus 7 mole per liter. That's equal to 10 raised to minus 14 mole square per liter square, or molar square, M square, capital M square. You remember this value, 10 raised to minus 14. So ionic product of water at a 298 Kelvin is a constant, and that's equal to 10 raised to minus 14. If you calculate the concentration of water, concentration of a pure water, concentration of a pure water is a constant, and that is equal to 55.55 mole per liter. 55.55 mole per liter. That's a constant. You calculate the concentration of a pure water in terms of a number of moles per liter. And concentration of water, pure water, that's a constant, and that's equal to 55.55 mole per liter. That means if you take 1 mole of water, 1 liter of water, 1 liter of water, there will be 55.55 moles of water. 55.55 moles of water. Okay? You take 1 liter of water. In 1 liter of water, there will be 55.55 moles of water. And that's a constant. Because the ionization is very low value, 10 raised to minus 7. What is it? 10 raised to minus 7? 1 by 10 raised to 7. 1 by 10 raised to 7. That is a negligibly small value. Negligibly small value. And therefore, concentration of pure water is taken as a constant. And that's equal to 55.55 mole per liter. Unionized water is equal to 55.55 mole per liter. That is the concentration of pure water. Okay, it's a constant. Then, another thing, that is the pH scale. You have studied this in the 10th standard. You have studied pH scale. You know, pH scale is a scale used, the scale used to express the concentration of H plus ions. Scale used to express the concentration of H plus ions. Let us see more details in the other classroom. You switch over to studio number 10. Let me stop now. Thank you.